Alright, good morning. How is everyone? Or how are you? Doing good, good. Glad to hear it. Alright, well, I hope everyone had a good break. If you got a few days off, that's awesome. I got caught up on grading and got some stuff done and even got sleep one day. Alright, so let's see. Let's talk about programming assignment 1. So PA 1 is graded, grades are posted. If you did not get any comments, then your code was beyond comment. It was basically perfect. And so your score reflects that, and there's no feedback in the comment block. If there were any deductions for any reason, I put comments in the comment block saying what the deductions were for. If you have questions about those, go ahead and ask here or in office hours. So general comment on PA1, fantastic job. Lots of hundreds, lots of close to hundreds, right? Almost everybody's code worked perfectly, which is great. The deductions tended to be for kind of silly things, having a function that was named something different, having an output that didn't look like what it was supposed to look like. But the actual mechanics of the linked list, dealing with the array, setting up the structure of it, those things were all fantastic. So if you did not succeed in getting PA1 to work, right, I tried to give you some feedback as to where it looked like you were in your code development. And it may be, that we need to talk and go over the whole idea of linking these nodes together to build a chain, because that's sort of the central idea. And if that's still fuzzy, then it's very hard to write code that works with that. If it was a matter of running out of time, starting too late, having a file get deleted and you didn't have time to recreate it, something like that, that's it affects your grade on this assignment, but that's a small part of the final grade. That's not so worrisome as far as what do I have to do to correct that. But if you feel like you're not sure what the deal is with a linked list, if it's kind of fuzzy to you, let's definitely sit down and talk in office hours and go through it, and try to nail that, because PA2 is exactly like PA1 except in the way that we manage memory. The other things that were exceptional in PA1 were the following. One, most people did a really good job commenting their code, okay? Interestingly, almost nobody commented their main program. And I didn't explicitly say put comments in your main program, and so most people didn't. You definitely want to comment your main, right? Your main programs were usually pretty complex. For a lot of people, that was where a lot of your time went. And so any code that you write, put comments on it, okay? But the individual functions, had comment blocks in the beginning describing the behavior of the function, the inputs, the outputs, that kind of thing, which was great. And most of the functions were commented, line for line, which was also great. And then every main program had that comment block in the beginning with your name and date and assignment, and so that was great too. Saw lots of really good coding style, consistent indenting. I didn't take off points for anybody, I think, for indenting and so on. So no, left justified code and stuff. So really good job on that. And this is going to help you down the road, right? This is going to pay off when you go on to a university and you start getting, these 20-page assignment prompts, and you potentially lose points because your output is different from what the teacher asked you to do, or you didn't name a function the right thing, or you didn't name your main program the right thing, or your make file had some issue, or there were warnings or things like that, right? You're getting really good practice for all of that. So keep up all those habits, and we'll keep pushing them in the assignment prompts. And when you transfer to a university and you start doing your programming courses there, you're going to be at a serious advantage by having done this stuff. And yeah, so as you work through these assignments, right? Typically they'll help you understand the underlying concepts better. So for PA1 and 2, linked lists should make more sense as you're going through, especially with PA2. I think that's really gonna kind of nail down the concept for most people. If PA1 didn't do that. But yeah, we can definitely sit down in office hours, draw pictures, go through code, and or you can ask questions in class, right, about linked list, because we're doing linked list for at least another week. PA2 I'll post towards the end of the week, but we're going to start building up the stuff we need today to eventually get through PA2. Let's see, what else can I tell you? Just really good job on the assignment. Almost everybody had it available for me to download, and a few people who didn't, I sent them emails, and some of them got back to me right away, and had a downloadable repository, so that was good. Yeah. So that's all I got to say on that. Comment being done right. Okay, cool. We're good. So any lingering questions on PA1? So on to the good stuff, pointers. And pointers are really what we're going to be doing in this course. 223 we're going to work in Java, and Java does not have pointers. I mean, it does underneath, but in the language, there's no such thing as memory access. There's no such thing as the address of a variable. That stuff is hidden from us. What should be the range of numbers? When you take in an integer, if you scan it with %d, you never need to worry about the range of it. I mean, an integer is just an integer, so it's any. If it's an illegal integer, you're never going to get to the point where you can actually use it in an if statement. So if you scanf with a %d and you type in some big long number, right, scanf will do something with it. But once you have an integer variable, it's a valid integer. It's not your responsibility to check to see if it's in a certain range. And certainly, anytime we talk about integer, we include negatives and 0 as well as positives. But don't manually check to see if it's bigger than maxint or smaller than negative maxint plus 1 or something like that. So pointers. Let's do this through some code. So you won't test it with two big numbers. No. And if I did, I don't think that checking to see if your number is bigger than the maximum legal integer, I don't think that would even work. Because if it's bigger than the legal maximum integer, it wouldn't be able to be stored in an integer variable. Unless you ingest into a long and then compare it to the largest int or something like that. But that's, like I say, that's usually not our responsibility. And if you do put a test on, definitely allow negatives and zeros. If you put a number that's slightly too big, right, one more than the largest legal integer, it'll come out as -1. If you put a number that's bigger than that, you'll get some other negative number, and eventually it'll roll over. But but if you put a number between roughly plus or minus 2 billion, it'll just take it as that number. That's interesting. Okay, I see what you did. Yeah, so in general, don't worry about that unless I ask you to deal with numbers that are too large. So let's just play with this. So let's just play around with scanf for a moment. Let's read in a character array using fgets. Let's scan it with a %d into a number, and let's see what that number does when we put in very large values. So a reasonable value, right, does that. A 9-digit number will work. A 10-digit number will also work. So 11 digits, that'll get us beyond the 2 billion largest integer. And it basically truncates it, right? So it takes the 32-bit number and it just chops it at 32 bits. And scanf still tells us that it managed to convert an integer. So again, if scanf is happy, I'm happy. That's kind of the general rule unless I say otherwise. Just like if you had typed in, extra stuff after this, it's still going to say, hey, I managed to convert an integer. So that's fine. Can you put a structure within a structure and call the variables from the internal structure with something like outer structure dot in structure dot in structure? Sure, absolutely. Yeah, and we will be nesting structures a little bit this course, more in other courses. But yeah, it's very common that one field of your structure can be a whole nother structure, and then you can just use nested dots. But we'll make that more interesting with pointers. Yeah, it does hurt a bit to think about, but it will hurt less when we do it the proper way with pointers to structures. It'll hurt a lot for a minute, and then it'll get better, and it'll suddenly like probably make you smile. It makes me smile. All right, so what's the deal with a pointer, right? If we have, an integer, we can say, show me the address of the integer with an ampersand. If we have something that's declared to be a pointer to an integer, we can say, what's the thing that's being pointed to by putting a star in front? Okay, that's our main, find an address, find the thing pointed to by an address. Repurpose some of this code. Nah, I won't. All right, so let's play around with a struct node. Yeah, the star in front is the value, and the ampersand gives you the address. Alright, so let's make a struct node. And our node is still going to have a data field, which will just make an integer. I'm getting super laggy here, or I'm writing really fast. So we'll have the data field. We're going to have a next field, and the next field is going to tell us where we find the next node. Now in PA1, the data field was an integer, and it gave us the index in our array. In PA2, our nodes are not going to be stored in an array. They're going to be stored somewhere in memory, but who knows where? Just some location in memory. And so the definition of our next field is going to be like this. It's going to be, wait for it, there we go. It's going to be a pointer to a struct node. So this can be a little disconcerting. To define a struct node as something that includes a pointer to a struct node, but that's totally okay. It's actually not recursive because this is a pointer. Now if we didn't have the pointer there, the compiler would throw up its hands and say, wait a minute. But this is just a pointer, it's just a memory address. It happens to be pointing to a struct node, which is what we're defining, but that's okay. All we really need to know when we're compiling this code is this is a memory address. So yeah, it basically points to itself, but more accurately, it points to something which is like itself. But when we actually have a struct node, the next field will be pointing to a struct node, but probably not to itself, but to another struct node. So it would be like having an integer that points to an integer, for example, which isn't quite as strange as this might look at first. Where is my CPU going? It's going to Xorg, yeah. And my screen recorder and a bunch on Zoom. Well, that's a bummer. Hey, maybe I need to upgrade my laptop. That's an idea. All right, so there's our basic struct node. So let's set this up. Alright, so that's what a struct node looks like. It's got a data field, and then it's got the address of a struct node. So let's make some nodes by hand. Alright, so I'm just going to go ahead and set some values in here, right? So our struct nodes do not need a valid field. We were using valid to know whether or not a struct node was in use. But for us, anytime we have a struct node, it's going to be in use. So the valid field is actually going to be managed by the operating system for us. And we'll see how in a bit. Alright, so I'm going to declare a sentinel to be a struct node. And I'm just going to arbitrarily set the data field to 42, set the next field to a hexadecimal number that I can easily recognize. And it may complain when I try to compile that, but that's okay. Yeah, it didn't like that, but that's okay. Alright, so let's run this. So we'll step through, we'll set the sentinel's data, and we'll set the next. let's look at the value of Sentinel, and you can see in GCC the data value is 42, the next address is dead beef, right? So it's just, you know, just a structure with some fields to it. Now that's not a valid memory address, right? If I try to examine that, I'll get a seg fault basically, saying that there's nothing available at that address. But, you know, I'm just giving it a value inside an assignment statement. That's totally legit. All right, so what do we got? We've got a Sentinel node. With a data value of 42 and a silly next value. Let's make some more nodes. Let's make a node called first. Let's make a node called last. And let's make a handmade linked list. So let's put a 10 in here. Let's put a 20 in here. And let's set up some links. So we'll have the Sentinel point to this node. We'll have this point to this node. And for the last node, I'm going to store null. Now null is defined for us inside standardIO.h. And that's the symbol we're always going to use when we want to represent, say, the end of a list, or a node that doesn't point to another node, or more generally a node that doesn't exist, right? We're going to use the value NULL uppercase, and that's the only value that we're allowed to use. You're not allowed to use 0, \0, *0, anything like that. NULL, right? So this was my null in PA1. And whatever system you're working on, NULL is guaranteed not to be the possible address of a valid memory location. It's always going to be something that will not actually be a memory address. And so we don't accidentally set something, you know, to point to a node and that address happens to be null, and so we think the list ends there. This is always a reserved address. Alright, so let's make 3 nodes, Sentinel, first, and last. Let's give them some data values and chain them together and see what they look like inside GDB. So, we'll give these things values. We'll give some data values in there, and now let's link these things together. So Sentinel should point to this node called first, which is probably not at location whatever. So how do I find the address of this node called first? How do I figure out where it's stored in memory? Use the ampersand. Perfect use of an ampersand. Alright, so that's going to build this first part of the link. Come on, there we go. That's going to set Sentinel to point to first. So it's technically pointing to first data, and this gets confusing sometimes, right? We're kind of thinking of first as an entity, right? It contains, you know, multiple fields, a data field and then a next field. But in reality, this is going to be pointing to some field inside here, probably the data field because we declared data first. So keep in mind that can flip around sometimes. Alright, next field is going to be the address of second. And then second next is going to be null. And so those statements should cobble together a linked list that looks like this. Or last, not second. Yeah, thanks. I'm hoping I can get through the next 25 minutes without my machine crashing, but it's starting to look dire. And if things like absolutely go away, just go ahead and hop back onto Zoom. All right, so let's play with this code. So let's compile it up. Let's run it. Let's next through until we get to our print statement. And so there's our Sentinel node. Data is 42. Next is E3C0. If I examine what's at that location in memory, I find the number 10. That's hex A. That's the data value of our first node. The next location has a 7FFF. The next location is an E3D0. The next location is a 7FFF. If I put these two words together to get a 64-bit address, and I look at what's stored at that location, I see the number 20, hex 14. Followed by a bunch of 5s, followed by a 0, followed by a 0. The Sentinel was stored at location E3B0. The first node was stored at address E3C0. And the last node was stored at address E3D0. So these are, big long string of hex digits before them, and then the interesting part, E3B0, C0, D0. And the Sentinel node's next field was E3C0, pointing to first node. Right, Sentinel next was E3C0. At E3C0, we found these two words pointing to E3D0, which was the last piece, and then E3D0 had our data field of 20, and then the next field, which was 0, which is null. So if we just look at a straight memory map starting at the address of Sentinel, it breaks out pretty nicely for us. There's the value of the Sentinel node's data field, that's 42. This is apparently just filler, and here's the address of the node that Sentinel is pointing to, E3C0. Down here at E3C0, we find that node's data value 10, another 4 bytes of filler, and then an 8-byte address for the thing that it points to, which is E3D0. And down here at E3D0, we find that node's data value 20, 4 bytes of filler, and then the 8-byte address it points to, which is all zeros. That's the end of our list. So if we do a memory dump like this, we can actually see our linked list byte by byte. And one thing that's worth noting in here is that, for example, for our Sentinel node, the data was stored at E3B0, the next 4 bytes were unused, and then the next 8 bytes had the address of the next field. There's this empty space in here. So why are there fillers in there? Right? An integer takes 4 bytes, and address takes 8, because we're on a 64-bit machine. That's only 12 bytes. Why is it using 16 bytes for each struct node? And this is a concept called word alignment. And it has to do with the realities of the physical implementation of a memory subsystem. The way that memory is organized, it's usually very efficient to fetch things in big chunks, say 64-bit chunks. So things that sit on an 8-byte boundary, we can access all at once. Even if we only want a single bit out of that 64-bit collection, we usually access the whole 64 bits. And it comes in very efficiently. There's a nice wide bus coming from the memory system to the CPU. And it's optimized so we can grab, a whole bunch of bits at once. But if we had an address which straddled one of these 8-byte boundaries, we would have to do 2 memory accesses to read it. We'd have to do 1 memory access to read this long word, and then a second memory access to read this long word, and then we'd have to throw away half of this and shift one over and put them together. And that's going to take a whole lot of work. And by simply putting in a filler so that this 64-bit address starts at an address that's congruent to 0 mod 8, I said it, we can more than double our performance. Now, if we're writing in C, we don't have to worry about that. But we have to be aware of it when we're doing something like this, where we're going through and looking at memory directly, and we're thinking, well, this is our data field, and so this should be our next field, and we try to look at that memory address and it's not valid. Why? Well, we have to know that this is filler, and this is where the next field begins. And we could find that out pretty easily. We could look at the address of sentinel.data, we could look at the address of sentinel.next, and you can see that even though data is only 4 bytes, the next field starts actually 8 bytes after the data field. That tells us there's filler in there. Alright, let me pick up these messages here. On our server, when I mimic what you're doing, I get cannot access memory. So you have to make sure that you're looking at a memory address that corresponds to something. So if you actually put in some code like this, right, where you have a structure declared and you look at the address of that structure, then you can start examining memory around that address. But this particular address probably doesn't work on the server. I think the server is a 32-bit virtual machine, so that's definitely not going to be accessible. And so yeah, that's probably the issue rather than permission. Double performance statement. Yeah, so basically, and this is more, a computer architecture subject, but let's just look at our memory. And so if I want to access, the contents of location 100, it's just this word right here. 104 is this word here. 108 is this word here. Well, the memory is actually organized a little differently. So this is how the memory is actually laid out, right? And we would think of it, if we're dealing with long words like integers or addresses, right? We think of it as, 4 bytes at a time. But the memory is actually set up like this. 8 bytes, 64 bits. Another 8 bytes, another 8 bytes, another 8 bytes. So if I try to access a memory address that starts at something that's divisible by 8, I just go out to the memory and I say, hey, give me these 64 bits. And boom, the memory does that really quickly. If I want something at address 118, I say, hey, give me 8 bytes starting at address 118, and boom, it comes back quickly. But if I ask for 8 bytes starting at address 104, I'm actually asking for these 8 bytes. And the memory subsystem is going to be accessed twice. It's going to be accessed once to get the 8 bytes starting at address 100, and then there'll be another memory access to get the 8 bytes starting at address memory 108. And then this will get shifted over, this will get shifted over, they'll get put together, the other pieces will get dropped. So it basically takes twice as many memory accesses to read an address that's not on a word boundary. And that is noticeable in the performance of code. So the compiler understands this, right, because it was written for a 64-bit machine with a certain architecture, and so it understands this, and it simply throws an extra word in here so that our memory address would actually be, you know, sitting right here on an 8-byte boundary. C has associative arrays. There's a library called DBM. Now it's GDBM, and that lets you spin out associative arrays. Word size is associated with hardware, right? So this is a different story on a 32-bit machine, perhaps. It depends on the memory organization, and even on older machines, right? The memory subsystem is still probably oriented on something bigger than 4-byte boundaries. Old days, right, early 80s, everything was 32 bits. Memory was organized in chunks of 32 bits. So as long as you were on a word boundary, right, where a word was 4 bytes, you were good. But if you tried to access something in the middle of a word, right, same thing, double memory reference. All right, it's a little bit of a sidebar, but we're going to be playing around with looking at memory like this, and there's a homework set posted, an online quiz that deals with these kinds of explorations in GDB. So those will pop up. All right, so let's look at dynamic memory. I still spelled it wrong. Dunamic, there we go. All right, so suppose we want to add something to our list. So we have our sentinel, we have our first, we have our last. So here's our linked list, same one we're working with. And let's make a new node. And I don't know, let's put a 500 in here. And let's squeeze it into the beginning of our list. All right, so so we'll set the data equal to 500. We'll let the new node point to whatever the sentinel is pointing to. And we'll have the sentinel point to the new node. New node is a struct node, so it's got to be the address of the new node. Alright, so let's just look at this in a memory dump. So here's the Sentinel node. It's got a 42. That's filler. It points to address E3D0. E3D0 has a data field of 1F4, which I'm assuming is 500 decimal. It's got filler, and it points to E3B0. E3B0 has a data value of 10, filler, and it points to E3C0, and E3C0 has a value of 20 and points to null. So that is our linked list, right? That's our list with the Sentinel node pointing to a node with 500, pointing to the node with 10. So far this code works great. Suppose I want to insert another node. So here's the problem. If I just put this code down here, let's put in a node with a value of 7,000. Right? This is not going to work. If I set new node data equal to 7,000, new node next equal to Sentinel next, I've got a problem. What this code is telling me to do is set new node data to 7,000 and set new node next equal to whatever Sentinel next is. And that's saying, well, let's just go ahead and have this thing point to itself, and that's kind of weird. So if I have my list looking like this, and I want to insert a new node before this, I need to make another box. Maybe I'll call it newer node and set that to 7,000 and have that point to new node and change my Sentinel to point down here. So I can do this, and I can insert a newer node and give it a data value and have it point where the Sentinel was pointing, and that will give me this list. Suppose I wanted to do this in a loop though. Suppose I wanted to read numbers from the user and keep creating new nodes and put them in the beginning, right? I'd have to call this, you know, new node and newer node and still newer node and really, really new node. And I need different variables each time that I want to create a new node. And this is the fundamental confusing thing for a lot of people about building a linked list on the fly. Where do we get these new nodes from? Because if I just say struct node, new node, right, that's just one node. So we need to dynamically allocate new nodes. And so this is where your friend malloc comes in. Or LLOC as close friends call. So I'm going to make new node a pointer to a struct node. And I'm going to say call malloc. And malloc is going to be like our get node function in PA1. Malloc is going to look in a pool of available memory, find a spot that's available, and then tell us where that spot is. And when it does that, it's also going to set something internally like a valid bit to say, hey, this spot's no longer available. Somebody has claimed it. Right? Malloc's going to handle that for us. So I'm going to malloc a bunch of bytes. The argument to malloc is an integer. It's how many bytes you want. How many bytes do we need for a new node? Well, we know from looking at it in the debugger that it's 16 bytes. But don't ever code a hard number in here, right? Instead, say size of the type of thing that you want. Struct new node. Struct node. And now, since new node is a pointer, I have to say star new node to actually refer to the node itself. And since new node is a pointer, I don't say ampersand new node to find the address of the node. New node is the address of the node. And now if I want to put in a node that's equal to 7,000, I simply give new node a new value, set its data to 7,000. And I can reuse this variable new node because each time that I call malloc, it points to a different location in memory. Okay, and this is the magic of dynamically allocating memory. Same name of the variable, new node, but it has a different location in memory each time that I assign it a new value. So when I make these statements down here, I'm manipulating a different area of memory from what I was manipulating up here. So I'm not stepping on my pre-existing node, I'm actually getting a new location. Alright, you need to include standard lib. So let's run through this. So there's a sentinel node. The sentinel node points to a node with this address. At that address we find this number. This is 7,000 in hex. So that's the data value of this newer node, right? The next value is filler. The next two values are a memory address. And if you look at that location, don't ever try to type these in by hand, just copy and paste. If we look at that location, that's the number 500, right? That's the data field of our second node. It's followed by filler, and it's followed by good old 7FF address. And at that location we find our 10, and that points to the node that we called last, which had a 20, and if we look at that location, there's our 20, and that points to null. So this is what we're going to be doing for the rest of our lives, or at least for the next few weeks, is using malloc to find a spot in memory where we can create a node. Right, and this used to be, you know, new index equals get node. Well, now we call malloc, and it's giving us a memory address, and that memory address is a spot that's available in memory, and so we can set the data field in the next field of that to create a new node in our list. And this works because every time we call malloc, we get a different location back from the function call. And each time it gives us a chunk of 16 bytes that we can use, it marks it so that when we call malloc again, it doesn't give us the same location, it'll give us a different location. And if you call, you know, malloc and ask for a bigger chunk of memory, you get a significantly different address. Right, so these are locations that have been marked for us. So we'll drill into this a lot more tomorrow, right? This is possibly, if you haven't seen this before, this is probably going to seem fuzzy to you. That's okay. We'll break this out in pictures more tomorrow, and we'll start putting together more code for this and working towards PA2. Yeah, if you call malloc in a loop, you'll basically suck up all the memory, and you know, something will happen. Don't try it on the server, but you can try it on your own machine. And it doesn't take too long, and you can malloc a whole bunch of memory. But you know, if you just try to call malloc with a big number, it'll give you back null, saying that there's no memory available. So that's the magic return value it gives you when there's not enough space to do that allocation. But if you allocate little chunks too many times, you run out of memory. All right. Have a good afternoon. I will see you tomorrow.